Let me talk a little bit about special relativity. Right now it is, 1900 plus or minus 5 years, right? Right about the turn of the century, there was this great, people were talking about the end of physics, the notion that physics was pretty much over. They were, cleaning up shop. Pretty much, Newton had figured out mechanics and calculus along the way. There were just a couple things that really they hadn't figured out. One of them was that we didn't really have a very good classical equation of black body radiation. We couldn't predict the intensity of the radiation with respect to wavelength. This, of course, led to Planck's equation, which led to quantum mechanics. Right, we're still figuring that one out right now. And then the second little thing, and this little bitty thing here was. There was this notion of the velocity of light with respect to ether. Ether was supposedly this medium that was very hard to detect, that light traveled through. So let's talk about that. That's where we're headed here. Okay. Maxwell's equations were sort of this victory of differential calculus, and he described magnetic phenomena. The stuff we learned in classes all sort of comes from that. It's algebraic approximations of these. But there are these four beautiful equations, and at the time, they were printing up T-shirts, and this was what they had on the T-shirts. The speed of light is 1 over the square root of mu naught epsilon naught, right? Now, the cool thing is that this is the formula that governs all things magnetic, okay? And then this is the thing that governs all things electrical. And so it was this beautiful thing that it was, the speed of light was 1 over the square root of these constants multiplied together. This epsilon naught, by the way, the force, the Coulombic force, we said it was KQQ over R squared, right? When you get to college, you'll realize that it's 1 over 4 pi epsilon naught, right? Times Q over R squared. And this is actually in our data packet. We just didn't use it because this is simpler, okay? Now, here was the great mystery. This is what they couldn't figure out, okay? Was what does light move through? Sound waves move through air, and ocean waves move on the surface of the ocean, and earthquake waves move through the Earth's crust, right? But what does light travel through? Well, they couldn't conceive that it didn't require a medium. We, of course, now know that it can travel through nothing. It can travel through a vacuum. It travels the fastest through a vacuum, in fact. But at the time, they believed it had to have a medium, and they called this medium ether. They proposed that there was something that we hadn't detected yet that was what carried light. And they knew that it had to be ethereal. And then, this is why it's called ether. Okay. It had to be fairly ethereal because the Earth moves rather rapidly, 19 miles a second. And it had been moving for 19 miles a second around the sun for at least a long time. In 1900, I think they thought the Earth was at least millions of years old. Right. So the idea was that there was this stuff. It was very ethereal, and the Earth moved through it. And with the Earth moving 19 miles a second, right? Light travels 186,000 miles a second. And so they actually devised a device that was sufficiently sensitive that it could detect the motion of the Earth through this wind, this ether wind, right? And this is the Michelson-Morley interferometer. And I've seen one of these in action. They're exquisitely sensitive. What you do is you have a source here. Some of the light, because this is a half silvered mirror, goes this way, and ends up here. Right, so one path is this way, right? The other path is this way, and then this way, right? And what you get is the light that traveled this way and light that traveled this way superimposed. If you change one of these paths by just the slightest amount, if you change it a half a wavelength, remember that that's the difference between constructive and destructive interference. And they do this in the book, they work out the math. But basically the idea is that this pathway, if there is an ether wind this way, this pathway takes a little bit longer. If light does travel through ether and the Earth is moving 19 miles a second around the sun, okay, this thing was sufficiently sensitive to detect that this path takes a little bit longer than this path. Well, so how do you detect that? What they would do is they'd set it up, and I think these things have to rest on isolation tables. They're so sensitive, you have to float them on air. And what they'd do is they'd take this thing and they'd set it up, and then they'd rotate it 90 degrees so that this path would become parallel to the ether and this would be perpendicular. They'd trade places. When they traded places, the path change would be larger than a half a wavelength. They knew this, okay? Well, so they set it up. They get the thing all, tuned up, right? They try it and they rotate it 90 degrees, nothing. It doesn't shift. There's no ether wind, right? Well, they try it in June. They try it in January. The Earth is never moving with respect to the ether. They don't detect the ether, right? So this is great, very perplexing, right? Well, there were several explanations of this that provided, right? The first explanation is that maybe all the ether in the universe orbits the sun with the Earth. This is, probably not true. The second explanation is that the Earth, as it travels through the ether, has a thin boundary layer of ether that stays very close to the Earth and doesn't move with respect to the Earth. It drags ether with it, right? So you ought to be able to float one of these in a balloon. I'm not sure whether they tried that, but higher in the atmosphere, maybe there'd be more ether wind, and lower there'd be less. Okay, that was another explanation. And then somebody named Lorentz proposed that the ether, as substances, solid objects, any matter travels through ether, it'll actually contract. That this thing parallel to the ether wind will contract, and therefore we don't notice that it's longer. Right now, that's actually what happens, but not because of ether. Okay, so they didn't detect this, right? So let's go. Here's this patent clerk, right? Albert Einstein went to school, studied as a physicist. Now he's a patent clerk, right? He starts to think. He thinks of this whole situation, right? And he thinks to himself, and this is Gedanken. It's just a German word for to think, right? He starts to think, and he says, well, gee, if we could catch up to an electromagnetic wave, which, why not, right? We can catch up to sound waves, and we can catch up to earthquake waves, and we can catch up to waves on the ocean, right? If we could catch up to an electromagnetic wave like light, what would we see? Well, we'd see a light wave sitting still. We would see electric fields and magnetic fields sitting still. There wouldn't be any charge distribution to make the electric field. There wouldn't be any currents moving to create the magnetic field. And this would, of course, be impossible. So if we could catch up to an electromagnetic wave, we would see something that's impossible. Now, there's nothing wrong with electromagnetic waves. Maxwell's theories predict that a changing electric field creates a magnetic field. A changing magnetic field creates an electric field, right? There's nothing wrong with it moving along at the speed of light. But if you could catch up to it, if you could put yourself in a frame of reference moving with this wave, you would see these things sitting still, and they can't sit still. That's impossible. So therefore, if you could catch up to it, you'd see things that are impossible, and that frame of reference is not possible. So he proposed that you cannot catch up to light waves. In fact, the simplest idea is that the speed of light is the same in all frames of reference, regardless of the motion of the source or the observer, that the speed of light is always, always the same. So he postulated, here are the postulates of special relativity. He postulated that these are true. The first postulate is that the laws of physics are the same in all inertial frames of reference. So then, what does inertial mean? Well, just inertial frame means that the law of inertia holds. So the acceleration is zero, right? You're not going in a circle because that's centripetal acceleration. You're not speeding up. You're not slowing down. You're moving in a straight line at a constant speed. If you are, then all of those frames of reference are the same. Another way to say this is there's no experiment you can do to ascertain whether you are moving and someone's sitting still, or whether they're moving and you're sitting still. If you meet another spaceship in space, you'll never ever win the argument, no, you're moving, I'm not. Okay, that's the notion here, right? The second, so this is where relativity comes from, right? All motion is relative. If you're moving forward, right, I could say you're moving forward, and you could say to me, no, you're moving backwards, right? It's all relative to each other, as long as we're moving at a constant speed. The second postulate is that the speed of light is the same no matter what the speed of the source or what speed the source or observer is going, right? Basically, I think this is redundant. I think it's just basically there's just one postulate here, right? The speed of light is a law of physics, right? If all laws of physics are the same, then the speed of light would be the same. Okay. Now, what this means is very, very strange, right? This means what Einstein is saying is that say we've got a roadway like this and we got a car. Okay. And you're sitting in this car And let's say you're going a wee bit fast. You're breaking the speed limit. You're going 0.9 the speed of light. Okay. As you travel at 0.9 the speed of light and you turn on your headlights, let's suppose you could see those photons. Remember, it's a Gedanken experiment, right? You would see those photons moving away from you at the speed of light. Light, whenever it's observed, is always going the speed of light. So you would see those photons moving away from you at the speed of light. Now, if we stood here with our heads apparently falling off our bodies, right? If we stood here observing this, okay, even though you're going 0.9 the speed of light, even though you see the light traveling ahead of you at the speed of light, we would see those photons traveling exactly the speed of light. Now, of course, they'd be blue shifted. There'd be a crazy Doppler shift going on here. Okay. In fact, everything in that frame of reference would be shifted would be very short. The wavelengths would be short. The car would be short. All this stuff, right? But I would see the speed of those photons traveling at the speed of light, exactly the speed of light. Okay. Yeah. So light, whenever it's observed, is always going the speed of light. Let's just keep going with this, right? Okay. Let's have two cars driving along, right? Okay, these guys would be like traveling this way. Let's suppose this guy's going 0.9 the speed of light. This guy's going 0.8 the speed of light. They're head-on collision, right? These drivers, of course, see the photons from their headlights traveling away from them at the speed of light. This person sees these photons traveling exactly the speed of light. Now, there's a crazy red shift there, right? Okay, these drivers would not see each other going what you'd predict 1.7 times the speed of light, right? These are all that, by the way, when you just do simple math like that, that's called a Galilean transform, right? There actually is a way to reconcile these things so that it's actually their relative velocity is less than the speed of light, right? But these guys I would see this car traveling toward me at less than the speed of light. I would see these photons traveling exactly the speed of light, okay? This guy would see these photons traveling away from them, the speed of light. This person would see those photons traveling the speed of light. Light, whenever it's observed, is always going the speed of light. Okay. Now, I saw this on the IB test from last year. So let's take a look at this, right? In an experiment in CERN in 1964, a neutral pion moving at the speed of 0.99975 C with respect to the laboratory decayed into two photons. And this is just a way that we write the speed of light, right? The speed of each photon was measured with respect to the laboratory. To describe how the result of this experiment provided support for a special relativity. Well, these photons were recorded as going exactly the speed of light. This one was going to the speed of light this way. This one was going the speed of light that way. Now, of course, for momentum to be conserved, this one would have to have a bit more energy and momentum than this one. But the speed that they traveled was independent of the speed of this pion, which is kind of cool. So that's the key concept here, is that the speed of light is always observed to be the speed of light. It does not depend on how fast the observer is going. It doesn't depend on how fast the source is going. It's always the speed of light.